Hello everyone, this is Dr. Lennon, and we're going to talk about two more tests for infinite series today, the divergence and the integral test. So the first of these is pretty obvious. So this theorem we'll call the divergence tests. So again, this is a test that can be used to tell us if a series will diverge, but it won't tell you if it converges. So basically, if you look at some series, the sum of a sub n from n equals, say, 1 to infinity, if this converges, then the limit of your terms that form the sequence, the numbers there, the a sub n's, that must go to 0. There's no other way. Otherwise, it's very easy to construct a proof that shows that that if your final terms don't go to 0, then eventually you could have a bound. The series would be bounded, and you could just add a bunch of constants to the end, so therefore it would go to infinity. So basically, why is this a divergence test? Well, this is an if-then statement, which means that the contrapositive will also hold true. So the contrapositive of this actually is the useful part that shows us when a series diverges. So the contrapositive says if this limit is not equal to 0, then the series must diverge. So equivalently, if the limit as n goes to infinity of a sub n is not equal to 0, then this series that you're looking at diverges. So that's why this is the divergence test and not the convergence test. The limit, if it's not 0, then we know the series diverges. Otherwise, we can't say anything about the convergence. We have to use other means to try and figure out if it converges. So let's go ahead and look at some examples. A lot of times you just eyeball the limit and you say, okay, well, if it doesn't go to 0, then you immediately quit and you say, okay, I'm done. So a lot of times implicitly in your head, anytime you look at a series, you're always kind of doing the divergence test first. So let's say use the divergence test to say the series diverges or is inconclusive. So let's look at the series from k equals 0 to infinity of k over k plus 1. So basically, we just look at the limit. So the limit as k goes to infinity of k over k plus 1, well, we know this limit just goes to 1. So thus, the series diverges. Right? Anytime that limit of your terms is not equal to 0, you can immediately say by the divergence test that the series diverges. Okay. So B, let's look at the series from 1 to infinity of 1 plus 3 to the k over 2 to the k. So again, we're just looking at the limit as k goes to infinity of 1 plus 3 to the k over 2 to the k. So that 1 is going to be insignificant, so basically this is just going to be the limit as k goes to infinity of 3 to the k over 2 to the k, which is basically the limit as k goes to infinity of 1.5 to the k, which we know goes to infinity. So the series diverges. Again, by the divergence test, the limit is not going to 0. So again, we know that goes to infinity just by the geometric sequence theorem that we looked at before. So thus the series diverges. Okay, so let's look at one of the most famous series. I think we've talked about it before, but this is known as the harmonic series if you just look at 1 over k from 1 to infinity. So again, this is just 1 plus a half plus a third, and so on. If you look at the limit, in fact, this limit goes to 0. So the limit of 1 over k as k goes to infinity, in fact, is 0. So what does this mean? A lot of people will jump to the conclusion, will say if it's 0, well then it has to converge. Well, that's not the case. When the limit is 0, the test is actually inconclusive. So the divergence test is inconclusive is all that we can say. We do not know whether it's going to converge or diverge based on this. This is why we have the need for some other test. But in fact, if you expected the series to converge, you would be wrong. The series does diverge. The harmonic series which is the one we're looking at, diverges. And just to show the fact that it could also converge, if you looked at the series of squares, 1 over k squared, which would look like 1 plus a fourth plus a ninth plus a 16th, and so on. Here the limit as k goes to infinity of 1 over k squared. This also goes to 0. So the test is inconclusive. But we will look in a second and show that, in fact, this series converges. So, in fact, the above converges. So, how can we show those things? Well, we can show those things by looking at the next test, which is the integral test. So the integral test is going to essentially kind of compare these things. There's a few ways to do it. We don't necessarily need the harmonic test, but a lot of times the harmonic test will kind of show where this comes from. So the idea of the integral test is we can, so the idea, I would say, is to use Riemann sums to compare series with integrals. And it's quite a good idea. So with that harmonic series that we looked at above, we can do that. So let's consider doing this with the harmonic series. Which is the sum of 1 over k from k equals 1 to infinity. So how do we do that? Well, what we want to do is we want to think about comparing this thing to a function. So consider finding the Riemann sum or let's say a Riemann sum for y equals 1 over x. So then what you've got is a picture, and you want to draw a bunch of rectangles. Again, we're just going to do it with the width of 1 for each of these rectangles. So if we have 1, 2, 3, 4, and so on, we'll go all the way out to, say, n, and maybe n plus 1. What's going on here is your 1 over x in the first quadrant here just looks something like this, right? You've got this type of picture, and when you're doing Riemann sums, what you're doing is you're kind of just making a bunch of rectangles. So this first rectangle you would have would go up here, and you would then get that, and then you would get this one, and this one. So in fact, these Riemann sums are a bunch of rectangles, each with width 1. And so we actually know that if we have this, if this is the curve y equals 1 over x, this first one is going to be 1, right? You have 1 times a width of 1. Then your second box would be, well, it would be 1 over 2 is the height times your width of 1. And then you would have 1 over 3 plugging in 3, 1 over 4, and so on. So the series for a bunch of these boxes, this Riemann sum, so if we looked at the boxes, S sub n here would just be 1 plus a half plus a third, and you would go all the way up until you got to 1 over n or 1 over n plus 1, something like that. And this sum of your S sub n's, or actually S sub n is already a sum, so we don't need that summation. If I called the terms a sub n's, then it would be the sum of the a sub n's, but S already stands for the partial sum. This thing is in fact greater than the integral, right? If we looked at the integral, the area below the curve from 1 all the way up to, say, n plus 1, we would get the area below the curve. So you've got all these little extra triangle-looking pieces kind of all over the top. So that's actually, in fact, making this sum greater than the integral from 1 to n plus 1. So if something smaller, in fact, diverged, if we knew this integral diverged, well, that means this is going to infinity, so that would mean S sub n would have to be bigger. So that's the conceptual idea for the integral test here. And in fact, if we're looking at a continuous positive function that's decreasing so that it isn't obviously diverging, then this is what happens. So this is the theorem, the integral test. So again, suppose f is a continuous positive decreasing function for, let's say, just x greater than or equal to 1. That's kind of like wherever your series is starting. And let's suppose our a sub k's are all matching up when you evaluate f at k the same way we saw when you plugged in those numbers. We were getting the same values that we had in our series. And this is for all the k's that you're looking at. In this case, they would just be the counting numbers. Then what's going to happen is your series is going to converge and diverge along with your improper integral. So it's going to go exactly the way that improper integral would go. So the series and your integral from 1 to infinity of f of x dx either both diverge or both converge. But it's important to note that the value of the integral is not necessarily the same as the value of the series in case they converge. Note the value of the integral may differ from that of the series. So let's go ahead and use it for the ones that we talked about above. So let's example say whether the series converge or diverge. So we're going to use the integral test to do that, although we already kind of know what's going to happen. So A, we have the series from k equals 1 to infinity of 1 over k. So basically what we're going to do is we're going to compare this to, we're going to look at the integral from 1 to infinity of 1 over x dx, which is the same as the limit as, let's say, let's say t goes to infinity of the integral from 1 to t of 1 over x dx. So one of our improper integrals. So we know this is the limit as t goes to infinity of the natural log of x from 1 to t, and the natural log of 1 is 0, so we know this is just the limit of the natural log of t as t goes to infinity. Plugging in, so this goes to infinity. So hence, the series diverges by the integral test. So let's look at the other one, the one that we saw that converged, and show that that does the same. So B, let's look at the integral from k equals 1 to infinity of 1 over k squared. So let's see. We're going to compare this again with just the integral y equals 1 over x squared. So we're going to look at the integral from 1 to infinity of 1 over x squared dx, and this is going to be the limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx. And in fact, this integral is quite easy, right, because it's just negative 1 over x. So this is going to be negative 1 over x from 1 to t. So what happens? Well, we get the limit as t goes to infinity of minus 1 over t plus 1, and we know 1 over t is going to 0, so this just goes to 1. So because the integral converges, we know that the series will also converge. However, the series does not converge to 1. That's quite clear, right? The series is definitely more than that because the first term is already 1. So by the integral test, so this series from k equals 1 to infinity of 1 over k squared converges. So all set there. So let's go ahead and look at a couple examples that are a little more interesting than that. So let's look at, let's say, the series where we're going from k equals 1 to infinity of k over k squared plus 1. So essentially this integral test just comes down to evaluating improper integrals. So if you have some practice at that, it's not so bad. So what are we integrating here? We're integrating from 1 to infinity of x over x squared plus 1 dx. So this is the limit as t goes to infinity of the integral from 1 to t of x over x squared plus 1 dx. So How is this done? Well, this is done using substitution, right? You want to let u be x squared plus 1, but we can kind of skip over that. So that's just a little review if you're forgetful. So the limit as t goes to infinity, and our integral is going to be 1/2 the natural log of the absolute value of x squared plus 1 from 1 to t. So this is going to be the limit as t goes to infinity of 1/2 the natural log of t squared plus 1 minus 1/2 the natural log of 2. And we know that this is clearly going to diverge because the natural log of a ever-growing quantity is going to diverge. So this equals infinity. So our series diverges by the integral test. Okay, let's look at another. Let's say the integral from k equals 3 to infinity of 1 over the square root of 2k minus 5. So what's going on here? Well, again, we're just going to compare it. Since our series starts at 3, we'll just start our integral at 3 as well. So we're just looking at the integral from 3 to infinity of 1 over the square root of 2x minus 5 dx. So this is going to be the limit as t goes to infinity from 3 to t of, maybe it's easier if we rewrite this 2x minus 5 to the negative 1/2 dx. And then we can go ahead and do our antiderivative. So this is going to be the limit as t goes to infinity of, what do we have? Well, we have 1/2, and then we're dividing by 1/2 and dividing by 2. So this, in fact, is just going to be the square root of 2x minus 5 from 3 to t. Let's check that by doing the derivative. You'd have a 1/2 in front coming from the antiderivative, then you'd have a derivative of 2 coming out, canceling that. So yeah, that in fact does work. So what does this evaluate to? Well, we know this is just going to infinity. It's going to basically the square root of 2t as t is going to infinity minus some finite number. So this is going to infinity. So this, so again, by the integral test, the series diverges. So one thing that comes out of this is basically we understand the convergence of a bunch of different things that look like polynomials, and this will be useful for comparison tests as well. So let's just call this the p-series test. So basically we know if we look at this series from k equals 1 to infinity of something that looks like 1 over x to the p. This is known as a p-series. Oh, I should be using k, not x. 1 over k to the p. Basically, this converges. So there's 2 results. So 1, it converges for p greater than 1, and it diverges for p less than or equal to 1. So basically things of that form, we know how they're going to behave with respect to convergence. So that's why we looked at the harmonic series. P was equal to 1, that's why it diverged. That's right on the borderline. That's kind of like the smallest p can be where it will still diverge. And if you look at something like 1 over k squared, p converged. The above, the last one we just looked at, we had a square root in the denominator, so that was diverging, right? If we look back up, Essentially, this is behaving like 1 divided by the square root of k, and that would be a power of k to the 1/2. That's why we saw divergence, because k was less than 1. And then here, what is this acting like? Well, you can kind of thinking of x over k over k squared plus 1. We can think of that as, well, how would k over k squared simplify? That would simplify to 1 over k, and like the harmonic series, that should behave in a divergent fashion. So this p-series test is kind of like a quick summary of any time we have one polynomial divided by another polynomial. We can kind of reduce all of those rational expressions to the p-series test. So that's going to be useful for evaluating convergence of series. Technically, you would have to prove this using the integral test, but we've kind of seen it through a bunch of examples. So it's good to keep this in mind. All right, so that's it for the integral test and the divergence test. It's Dr. Lennon signing off.